the math that predicts when things fall apart. Collapse never arrives without warning. It announces itself quietly, long before the break. But only mathematics knows how to listen. To understand how failure can be predicted, we need to look past headlines and triggers. Systems rarely collapse because of one event. They fail because internal patterns shift in measurable ways. Stress leaves fingerprints. Instability has a shape. The architecture of breakdown follows recognizable pathways, even when the specifics differ wildly across domains. What destroys a financial market shares mathematical DNA with what destroys an ecosystem or a power grid. The surface details diverge, but the underlying dynamics converge. This convergence is not coincidental. It reflects fundamental truths about how complex systems behave under sustained pressure. When we strip away context and examine pure structure, patterns emerge that transcend individual cases. This matters because modern systems assume collapse is unpredictable. Accidents, crashes, crises, they are framed as surprises. But mathematically, many failures follow the same trajectory. Variance changes, correlations tighten, recovery slows. These transitions unfold according to principles that can be observed, measured, and interpreted. The randomness we perceive is often an illusion born from insufficient observation. What appears chaotic at close range reveals order when viewed through the right mathematical lens. The challenge is not that collapse defies understanding, but that we have trained ourselves to look in the wrong places for the wrong kinds of evidence. At first, the signals are subtle. Small disruptions take longer to fade. Fluctuations become asymmetric. The system still functions, but it struggles to return to baseline. This is not noise. It is fatigue. The machinery of self-correction begins to labor under invisible weight. What once required minimal effort now demands disproportionate resources. The system compensates by drawing on reserves, masking the deterioration beneath continued performance. To external observers, nothing appears wrong. Outputs remain within acceptable ranges. Deadlines are met. Standards are maintained. But internally, the margin for error shrinks steadily. The buffer that once absorbed shocks grows thinner with each cycle. This erosion happens gradually enough that no single moment triggers alarm, yet cumulatively it transforms the system's fundamental character. As pressure builds, behavior changes again. Components synchronize. Independent failures begin occurring together. Diversity disappears. The system starts moving as a single body. This looks orderly, but it is a warning sign. When parts that should operate independently begin moving in lockstep, the system loses its ability to distribute risk. A problem that would once affect only one component now propagates instantly across the entire structure. This synchronization often emerges from rational optimization. Efficiency demands coordination. Waste reduction requires alignment. But taken too far, these improvements eliminate the redundancy that provides resilience. The system becomes brittle precisely when it appears most refined. The math does not predict the trigger. It predicts readiness, the moment when any trigger will do. Collapse is not about what happens. It is about what the system has become. And long before anything breaks, the numbers already know. As systems approach collapse, recovery time becomes a clearer signal. After a disturbance, the system takes longer to stabilize. Corrections lag. Overshoots increase. What once snapped back smoothly now drifts. The restoration of equilibrium, previously swift and automatic, becomes sluggish and incomplete. Each perturbation leaves lingering effects that compound over time. The system never fully returns to its original state before the next disruption arrives, creating a ratcheting effect where baseline conditions progressively degrade. This phenomenon is measurable. Mathematicians call it critical slowing down. It appears in ecosystems, financial markets, power grids, and even the human body. The system is losing its ability to respond quickly because its internal flexibility is disappearing. The mechanisms that once absorbed change are themselves being transformed. Feedback loops that stabilize become feedback loops that amplify. Buffers meant to dampen oscillations instead transmit them. The architecture designed for resilience begins operating in reverse, converting advantages into liabilities. This reversal happens not through failure of individual components, but through subtle shifts in how they interact. The parts still work. The relationships between them do not. At the same time, variance begins to rise. Small fluctuations grow larger. Extremes become more frequent. The system spends more time near its limits. These changes often go unnoticed because averages still look normal. Aggregate measures conceal distributional shifts. Mean performance masks increasing volatility. The center holds while the tails extend, creating an illusion of stability even as risk concentrates at the boundaries. This statistical camouflage makes variance increases particularly dangerous. Decision makers reviewing summary metrics see continuity, where detailed analysis would reveal transformation. The comfort derived from unchanged averages becomes a trap, preventing recognition of the deeper instability taking root. Correlations also tighten. Parts that once behaved independently begin moving together. Diversity collapses into synchronization. This feels efficient, but it is dangerous. When everything moves together, nothing can compensate for failure. The system loses its ability to maintain function through substitution. If one pathway fails, alternatives fail simultaneously. If one market segment drops, correlated segments follow. The independence that provided safety margins evaporates, replaced by a couple dynamics that ensure localized problems become systemic crises. This coupling often results from removing perceived inefficiencies. Redundant pathways are eliminated. Alternative approaches are standardized. Backup systems are consolidated. Each optimization makes perfect sense in isolation, but collectively they weave a web of interdependence that transforms minor failures into catastrophic cascades. What makes these signals powerful is timing. They appear before collapse, not after. They are not predictions of events, but measurements of vulnerability. The system is becoming fragile, even if performance remains high. This temporal advantage is crucial. It means intervention remains possible during a window when the system still functions normally. The opportunity to act exists precisely when action feels least necessary, creating a psychological barrier to effective response. The challenge is convincing decision makers to treat invisible vulnerability as seriously as visible failure, to invest in prevention when nothing appears broken. Mathematics provide the evidence, but translating mathematical warnings into institutional action requires overcoming deep-seated cognitive biases that discount future risks in favor of present performance. Most observers miss these signs because they are not dramatic. They look like minor inefficiencies, temporary slowdowns, normal variation. But mathematically, they are warnings. The subtlety works against recognition. Humans are wired to respond to acute threats, not chronic deterioration. A sudden crash commands attention. Gradual slowing does not. Yet the gradual changes contain far more predictive information. They represent the actual structural transformation, while acute events are merely consequences. Learning to treat slow signals as urgent requires retraining intuition, building systems that elevate mathematical indicators to the same priority level as experiential alarms. The system is not failing yet. It is preparing to fail, and preparation leaves traces that numbers can see, even when people cannot. The conflict peaks when these warning signals are recognized but dismissed. Leaders see the numbers, but incentives push them to ignore what they imply. Acting early feels unnecessary. Acting later feels inevitable. This is the emotional breaking point, the moment when knowledge exists without action, when models show rising fragility, yet decisions continue as if stability were guaranteed. The system is still functioning, so urgency feels irrational. Performance metrics remain acceptable. Stakeholders remain satisfied. The pressure to maintain current operations overwhelms abstract warnings about future vulnerability. This creates a peculiar paralysis where everyone involved possesses the information needed to prevent catastrophe, yet organizational dynamics prevent that information from triggering appropriate responses. Mathematically, this is the most dangerous phase. The system has entered a narrow corridor where small interventions can still restore flexibility, but waiting even slightly reduces the available options. Delay hardens vulnerability into destiny. The cost of intervention rises exponentially with time. Actions that would have been simple and inexpensive early on become complex and costly later. Eventually, they become impossible. The window closes not through a single decision, but through accumulated inaction. Each day of delay slightly narrows the range of viable responses until the only remaining option is managing collapse rather than preventing it. This progression is deterministic once the warning signals appear, making early hesitation mathematically equivalent to choosing eventual failure. What makes this conflict persistent is ambiguity. The signals do not specify how collapse will happen. They only show that it can. Without a clear threat, warnings compete with optimism, habit, and short-term reward. Human psychology demands narratives. We want to know the specific mechanism of failure, the exact trigger, the precise timeline. Mathematics offers none of these comforts. It provides only probability and vulnerability, leaving the imagination to fill in details that cannot be known in advance. This gap between what models can predict and what decision-makers want to know creates space for denial. If the warning cannot specify exactly what will fail, perhaps nothing will fail at all. This reasoning, while psychologically comforting, is mathematically backwards. The lack of specificity reflects a universality of the risk, not its absence. As pressure continues, the system's ability to absorb change evaporates. Interventions that once would have worked now cause disruption. The window closes quietly without ceremony. The system crosses into a state where restoration becomes indistinguishable from collapse. Attempting to reintroduce flexibility destabilizes operations. Trying to reduce synchronization breaks essential coordination. The very interventions designed to improve resilience trigger the failures they were meant to prevent. This phase represents the true point of no return, though it often goes unrecognized until long after it has passed. The system remains functional, but it has lost the adaptive capacity needed to respond to its own rescue. It continues operating only because conditions remain stable, a stability that cannot last but whose end cannot be controlled. The conflict is not ignorance versus knowledge. It is timing versus hesitation. And hesitation is mathematically expensive. The resolution comes when prediction is redefined. Mathematics cannot tell us exactly what will fail or when, but it can tell us when a system is becoming unsafe. That knowledge is enough, if it is respected. The shift required is philosophical as much as technical. We must accept that preventing collapse does not require predicting it in detail. Knowing that a system is entering a vulnerable state provides sufficient justification for intervention, even without certainty about specific failure modes. This acceptance demands humility, a recognition that perfect knowledge is unattainable and that acting on imperfect information is often the most rational choice. The alternative is waiting for clarity that arrives only after options have disappeared. Designing with early warnings in mind changes behavior. Action is taken when signals appear, not when collapse becomes visible. Flexibility is restored before rigidity hardens. Diversity is protected before synchronization locks in. This approach feels conservative. It sacrifices short-term efficiency for long-term survival. But mathematically, it is rational. Preventing collapse requires acting before certainty exists. The calculus is straightforward once the time frames are understood. Short-term cause of intervention pale against long-term cause of collapse. Efficiency gains from optimization cannot compensate for catastrophic failure. The mathematics consistently favors caution when warning signals appear. Even though institutional incentives often point in the opposite direction, the deeper lesson is uncomfortable. Waiting for proof is often waiting too long. Systems do not announce their breaking points clearly. They whisper them through data. The discomfort stems from embracing uncertainty as a reason for action rather than inaction. Traditional risk management waits for evidence before responding. Mathematical prediction of collapse demands the opposite. Respond to evidence of increasing vulnerability before concrete threats materialize. This inversion challenges institutional norms, regulatory frameworks, and individual psychology. It requires building systems that reward precaution and penalize hesitation, even when precaution cannot point to specific disasters prevented. The victories are invisible, measured in catastrophes that never happened, making them politically and economically difficult to defend. Learning to listen to those whispers is not about prediction. It is about humility, recognizing that stability is conditional and that the cost of delay rises faster than intuition expects. The math can warn us. What happens next is a choice. Subscribe to join the journey. The math